This seventh lecture is yet another way that we look at environments. And sorry, but we have to add another term here that essentially means the same thing. So there's our usual and sedimentary environment diagram. You've heard me call them environments of deposition or EODs, but now I'm going to say that we also sometimes call them facies. They all mean the same thing. So for instance, if you're used to in this diagram saying that's the delta environment or that's the organic reef environment, it can also be the reef facies or the delta facies. Another picture here saying essentially the same thing, but now we're going to look at a specific suite of facies in the shallow marine area, because there's one thing that's important about sea level that I'm going to get to in a couple of slides. So if you look at this picture right here, you have the land environments off to the left. The ocean starts right there where the brown meets the bluish color, and then you can sort of see the water here, and the sediment at the bottom of the ocean has sands, shales, or muds, and limestones. And so they've called them the sandstone facies, or the shale facies, or the limestone facies, or sometimes it's sand facies, mud facies, limey facies. What you need to see here, though, is that the environments, even though this is all what we called the shallow marine environment before, they have their little sort of sub-environments lined up in very regular order from each other. Okay, as sea level moves up and down, these environments are going to track them with that sea level. Here's another view of essentially the same thing. Here the land is off onto the right side. You can see the green land, the river flowing in and making this delta, but the sediment in the shallow marine area is sands, shales, limestones. And this doesn't, even though it's shown here, right here, just building up in place in one place, one of the things that we know is that the level here, the level of the ocean, where a boat would be, where you'd be swimming on top of the ocean, it doesn't just stay in one place. It moves. And when it moves, those environments are going to move as well. So here we are in that Florida Keys picture again. Shallow water right there. This person has built several structures on his little island that basically he's expecting sea level to stay exactly where that is right now in order to, well, stay alive, stay up here. We've built multi-million dollar highways that are a certain number of feet above the level of the water. During the human lifetimes, that probably won't change that much. But remember, in geology, we have millions of years of time, and one of the things that we know is, and there's that statement at the top of the slide, sea level is never constant. It is always moving up and down, always. And as it does, those facies environments do as well. So, this slide here, one of the truest statements that you can make, sea level never changes, never stops changing, excuse me. So think about it. If you've ever been to the ocean, you see that waves are crashing into the shore. Sea level goes up and down a few inches, few feet. The tide comes in, tide goes out, high tide, low tide, that can be many feet. But for us, what's important is in the red. Sea level goes up many hundreds of feet over several thousands or millions of years. And then it goes back down. There's two major reasons, and we'll talk about these the rest of the course. Basically glaciers and what we call plate tectonics. Sea level never stays the same. Never stays the same. So, what are sea level changes? So we call these things by two different names, principally transgression and regression. So look at the left side first. Transgression is sea level rise. If sea level rises, we say it has transgressed the land. And so the coastline moves inland. So if the beach is right here, if sea level goes up 20 feet, well, the place where you're going to be on the beach and still dry is going to go inland. So that we say all of those facies move inland as well. Regression is just the opposite. So if you want to streamline your studying, memorize one of them. Transgression equals sea level rise. The coastline moves inland. The facies move inland. And then regression is just the opposite. Here's an example to show how ice, or basically climate change, affects sea level. If ice grows, if we start an ice age, sea level drops because the water, instead of being in the ocean, gets tied up as ice on land. And of course, it makes all the sea level everywhere around the whole globe change. If you look at this slide here, it's a graph, and look at the different axes. So the bottom axis is thousands of years ago. We live on the extreme right side of this diagram. So that's 0,000 years ago, or today. And if you go back in time, what the line is graphing is shown on the y-axis here, mean sea level. So notice present level at the top is today. And if you go back 2,000 years, 4,000 years, 6,000, 8,000, notice sea level is much lower. It drops by 20 meters. Remember, a meter is a little bit over 3 feet, so that's over 60 feet. 40 meters, 60 meters, 80 meters as you go back here. And this then is indications of sea level has changed. So from about 18,000 years ago, sea level was really low because it was all tied up in the last ice age. When that ice age melted, sea level rose, flooded the land till we're about here. The next slide is one showing global sea level effects, two different things. So there's the map that you know of, and the black line would be the coastline today, but notice there's prominently marked here the coastline 18,000 years ago to go with that slide we just saw in the previous one. So 18,000 years ago, sea level was much lower. So think about it. Florida was much bigger. All these states along the coast here were much bigger. Texas was even much bigger. Now, if we were to melt our polar ice caps today, then the coastline would be what happens. It moves inland. Sea level would rise, and it would go this way. So all of Louisiana would be gone. All of Florida would be gone. The beach would be way up here in Missouri. From Wisconsin, it'd be a short drive, easily done in part of a day, to get to the ocean here. As it does that, think just about the beach. If the beach is this black line, and it's right where the ocean meets the land, and it's all that sand, it was down here, now it's here. If we melted the polar ice caps, it would be here. If sea level is going back and forth, then those facies are as well. Just another picture. The black line is the present day shoreline, and up here, and then in the past this way. All right, so there is some relationship that shows how the sea level rise and fall ends up giving us rocks. It's going to be called Walther's Law, but let's look at another slide here. And this one's a little different. Notice it has the same sort of thing, facies in the ocean this way, but notice here, instead of them being stacked directly vertically, so they're color-coded, they are all in motion. So look at the bright yellow color. That's the beach. When this first was being deposited here, there was the beach. But as sea level goes up, see the arrow going up? The beach just keeps following that area where the waves crash and do that, and so they move inland. So if sea level rises, all the facies go towards the left. and then that goes by the shallow marine facies, etc., etc. So this is just a slide from a different textbook showing essentially the same thing. Well, we can look at ancient rocks and tell that this has happened. So you're looking at a picture in the Grand Canyon. There are some burrows for scale, and there are different rock types that these are the names that they've been given: the Tapete sandstone, the Bright Angel shale, and the Muav limestone. So in other words, sand, mud, limey mud. And when they're stacked like this is saying that at this time, in this place, sand was deposited, and then later mud was put on top, later limey mud. It's an indication that sea level rose there. And so we make these little triangle shapes like this to say that rocks in this part of the cliffside right here indicate that sea level has risen up through that time. Turns out that geologists if you look at through the Grand Canyon or rocks anywhere, we see examples of many, many, many transgressions and regressions. Because just as we can see sand, mud, and lime stacked on top of each other, above this cliffside, not shown here, would be more lime, mud than sand, and show a regression, back and forth, back and forth. Well, we call the transgression evidence a fuss, or a fining upward sequence. Basically, the rock types, the sediment types get finer. So notice in the upper picture, there's our facies: sand at the beach, mud offshore, and then limestone way out here. Notice as you go down from A to B, sea level has risen. What does that mean? That means that the beach is moving onto the land. Notice here, the beach would be right where the water meets the brown, so you could walk right up to there and not get wet. It moves. Let the sea level keep rising, and it keeps moving, moving, moving like that. And then, if sometime in the future you were able to dig a core or a hole way out here and through all the rocks and then look at them, you would see them stacked with sands, muds, limestones, indicating that sea level has risen. If you go back to that previous slide, then there it is. Sands, muds, limestone. Anytime you see that stacking of rocks, it indicates sea level has changed. And one of the things geologists have discovered is that, sea level never stays the same. It is always either fining upward or it is coarsening upward. Again, remember, if sea level goes up, it can also come down. And when it comes down, notice the same process. You have time going down this way. Take a core of rock here. Notice it's the same three rock types: limestone, shale muds, and sandy sandstones, but notice they are stacked differently. Here, they are stacked with the sand on the top as opposed to on the bottom. And so if we were to draw it, we'd have a little triangle, an upside down triangle like that. This is then Walther's law. So a man named Johannes Walther from the mid-1800s, notice he is the second scientist we've talked about in this class. We've talked about Hutton and uniformitarianism, and now Walther and sea level change. And one of the things he said for us is that if you have a given, sea level has risen and fallen many times, boom. Second given, if that happens, facies will migrate with sea level. If those two things are true, and they are easy to accept, then the facies that are next to each other, so side to side, look in the diagram, to the left and to the right at any one time, over time, they get stacked vertically. So horizontal facies. Notice here the lime, the shale, the sand are side by side. They're horizontal. But over time, they get stacked vertically. And vertical rocks are what geologists see. So the last little picture is essentially saying the same thing. The same facies you find side to side, so this arrow is laterally, we're also present vertically. We call that Walther's law.